Did you know there's around 37,000 known near-Earth asteroids, or NEAs? We've even visited a couple of them with Japan's Hayabusa 2 mission and NASA's DART. Exploring more NEAs and increasing our knowledge of these objects will require many more visits, but large missions are expensive. Enter CubeSats. These are very small satellites based on a cube roughly 10 centimeters on a size, hence the name. This small cube is 1 unit or 1U in CubeSat speak, and 1U cubes can be stacked together to create larger satellites. For example, a 6U CubeSat constructed from 2 by 3 of the smaller units stacked together to carry more payload, do more science, and so on. Typically, CubeSats don't have a lot of anything on board, including propulsion. The whole goal being to go small and light and to allow students and others to learn how to make and launch satellites and do some interesting science without breaking the bank. Could we use CubeSats to visit near-Earth asteroids? There's a super interesting paper in Remote Sensing suggesting a method of doing just that. We know quite a lot about the 37,000 NEAs, including very detailed orbits for most of them. The idea is to park a CubeSat at a nodal point in the orbit of an NEA and simply wait for it to fly by so we can observe it. Getting the CubeSat to the right point in space is a major challenge, but the paper suggests using amazingly efficient ion thrusters. Once you're out in space, ion engines don't require you to carry chemical fuel, and you can power them with solar panels, making them ideal for use with a CubeSat and allowing you to position your CubeSat to lay in wait for its intended NEA. Given the low cost and size of CubeSat missions, they're often launched on rockets with other payloads as their primary mission, so launch costs are low, in addition to the reduced build cost. The paper also takes a detailed look at the most efficient configuration of ion thrusters for a mission like this, the best way to insert the CubeSat into the required orbit, and provides a potential target list of NEAs. I'll include a link to this cool paper in the description so you can check it out for yourselves. I will see you back here tomorrow. Are there asteroids hiding in the orbit of Venus that could pose a threat to Earth? That was the question that researchers from Brazil, France, and Italy set out to answer. We've been doing a pretty good job the past 2 decades or so of mapping asteroids outside of Earth's orbit, such as those in the main asteroid belt and the Trojans out in Jupiter's orbit. But asteroids that co-orbit with Venus could be very hard to detect. These asteroids hide in the sun's glare, meaning they can only be detected at certain times during their orbit. We currently know of 20 co-orbital asteroids of Venus, but here's a case where we don't know what we don't know. How many more are there? A complicating factor is that because of the chaotic nature of the orbits of asteroids like this, our observations can only predict the orbits out to about 150 years before the dynamics become too hard. The researchers built a model with 26 Venus co-orbiting asteroids in it and evolved the simulation for 36,000 years based on the dynamics of the major bodies in the solar system to see whether any of their simulated asteroids could have a close encounter with Earth. They also checked to see whether their simulated asteroids would be visible from Earth using the upcoming Vera Rubin Observatory. They determined that there would be close encounters with Earth, and perhaps more worrying that the asteroids would only be visible during their closest approach with us. Rubin will also have many other tasks, and the paper suggests that a spacecraft in orbit around Venus might be the best way to map out these co-orbiting asteroids, so at least we'd have a clear idea of how many we're dealing with. The paper's been submitted to the journal Astronomy and Astrophysics, and I've included a link down in the description. In 2027, NASA hopes to launch its MUSE mission to study the corona, or outer atmosphere of the Sun. The mission came a step closer last week when MUSE passed its Critical Design Review, or CDR. The CDR is a review of a mission conducted by an independent team of subject matter experts from both within NASA and outside the agency. This review examines hardware, software, and firmware at system and subsystem levels to ensure the mission can be successfully fabricated and will achieve its objectives. The review looks at almost every aspect of a mission you can think of, from the design itself to compliance of the proposed design with requirements for mass, power, reliability, the proposed facilities that will be used for constructing the spacecraft, and the instruments along to software and quality assurance. Once the CDR is passed, the mission can move into the fabrication phase, and that's where MUSE is now headed. The corona of the Sun is a mystery to scientists because it is so hot compared to the surface. You probably know the surface of the Sun is around 5,800 Kelvin, while the corona has temperatures from 1 to 2.5 million Kelvin, not what you'd expect as you get further away from the source of the Sun's heat. MUSE stands for Multi-Slit Solar Experiment, and it will obtain spectroscopic images of the Sun 100 times faster than currently possible. We can use that data to understand how the corona is heated, as well as give us insights into solar storms and events on the Sun that can cause significant damage to satellites and other infrastructure here on Earth. Another record for the James Webb Space Telescope last week, as it observed light from a galaxy emitted just 280 million years after the Big Bang, making it the most distant galaxy ever detected. JWST's unique combination of a large 6.5 meter mirror and the latest infrared detecting technology means it's much better equipped to find distant galaxies in infrared light than, say, the Hubble or Spitzer space telescopes were. A large part of JWST's mission is to map the earliest galaxies in the universe so that we can understand how galaxies form and evolve. Almost immediately after its commissioning phase, JWST began finding galaxies from the first 500 million years of the universe's existence, and has continued to push further and further back in time. The latest galaxy is MON-Z14 and was found from a spectroscopic survey of high redshift galaxy candidates. The Z14 refers to the redshift of the galaxy with an actual redshift of Z equals 14.4. We're looking at the universe as it was 280 million years after the Big Bang. It's worth pointing out that converting from this redshift number to an age of the universe does require a cosmological model, and there do seem to be some issues with our current understanding of cosmology. As far as galaxy evolution goes, astronomers didn't originally expect to find many, if any, galaxies this early in the life of the universe. The spectrum from MON-Z14 also reveals that the light comes mostly from individual stars and not from a supermassive black hole accreting material at the galaxy's center. In addition to that, the nitrogen to carbon ratio in the galaxy is very similar to stars that we see in ancient globular clusters in our own Milky Way, leading astronomers to wonder how galaxy evolution is connected over such vast epochs of time. As always, the observations from JWST create many new questions, but as we get more and more data from this amazing observatory, the hope is we'll be able to answer many of them. I've glossed over a lot of the details here to keep the video short, but you can check the paper for yourself at the link in the description. Where did the moon's magnetic field go? The history of magnetism on the moon has long been an area of active research for scientists. The moon no longer has a magnetic field, but there are rocks on the surface of the moon showing evidence of a very strong magnetic field in the past. We expect that the moon had a weak magnetic field early in its evolution, caused by a dynamo effect with its molten core, but this field would have been nowhere near strong enough to create the magnetism we observe in some moon rocks. Various theories have been proposed to explain how the field could have been so strong in the past. One idea is that during the first billion years or so of the moon's existence, giant rocks sank through the moon's mantle and caused an intermittent field. A second theory is that meteorite impacts created a dusty plasma that magnetized nearby rocks. New research just published in the journal Science Advances on May 23rd takes the plasma idea much further. Using detailed computer simulations, the researchers were able to show that a large impact on the moon, coupled with the weak magnetic field at the time, could have created a very strong magnetic field on the opposite side of the moon from the impact. A secondary effect would have been a pressure wave caused by the impact passing through the moon, causing electrons in the rocks on the opposite side to be excited during this time. The electrons would have oriented to the temporarily much stronger magnetic field and kind of baked this into the rocks before the magnetic field dissipated again. With this whole process possibly lasting for just 40 minutes, according to the research. The astronomers note that much of the magnetism that's been observed in moon rocks is found near the lunar south pole on the lunar far side, and on the exact opposite of this spot lies the Imbrium Basin, one of the largest impact basins on the lunar surface. Confirming this theory would mean sampling rocks from the lunar south pole region looking for signs of the shockwave and magnetism. Artemis is supposed to explore the region of the moon, although with funding up in the air, we'll see whether that happens anytime soon.